Hello, in this video we're going to talk about molar bond enthalpies and how you can use them to determine the enthalpy change for an overall reaction. So this is another way to estimate delta H for a reaction, the overall enthalpy change. And so previously we did this with enthalpy of formation values, where you know the energy change to make 1 mole of a compound from some standard state, and then you can compare that for a reaction. But what we're doing here is something different. Here we're using the bond enthalpies, the enthalpy change required to break or form a particular bond, and we're using that to figure out overall enthalpy change for a reaction. Using the bond enthalpies is less precise than the enthalpy of formation values. You get numbers that are a little off, but it has the advantage that you can use the bond enthalpies for any compounds. You don't have to have a compound where the enthalpy of formation value has been determined. So it has some advantages as well. Ultimately, it's just another way to do this that I want you to know how to do. So here's the idea here, is that if you have chlorine gas, for example, and you're going to break this bond into 2 monoatomic chlorine atoms, there's some energy required to do this. And the enthalpy that has to be put in here in order to break this bond is 242.7 kilojoules per mole. And that's an experimentally measured value for this type of bond. And then say you're going to break an oxygen-oxygen double bond. Well, that requires more heat to break that, so a higher enthalpy value. And then so on and so forth. If you want to break the nitrogen triple bond, that's even more heat. And then if you want to break the bond between HCl, here's the value for that. That's a single bond that you're breaking. Okay. As you may have noticed, the bond enthalpy value for a triple bond is the highest, and a single bond is the lowest. And this is because a single bond is the weakest bond, and so it requires less energy to break, whereas a triple bond is the strongest bond we have, and that requires the most energy in order to break it. So these bond enthalpies are phrased in terms of energy required to break a bond. If you then reform the bond, then that energy is released. But we're phrasing these as energy to break the bond, so it's an endothermic process. Okay, so we've determined a set of bond enthalpies, and these are averages over a number of different compounds that contain these bonds. And so ultimately you'll just pull the value off of this list. Notice all these values are positive because this is phrased as energy to break a bond, which is endothermic. Okay, so then how do we use these to figure out overall enthalpy change? So we imagine that a reaction proceeds by breaking all the bonds in the reactants and then using these atoms to form all the bonds in the products. So you basically disassemble the entire molecule in your head. This is not actually how chemical reactions work, but this is how we can use the concepts here. So imagine you disassemble every atom from all the other atoms, and that requires a lot of energy input in order to disassemble all those atoms, break all those bonds. And then you reform all the bonds, which releases a bunch of energy. And then you see what the overall difference is, and that's your overall energy change for the reaction. And so that's phrased here as energy required to break all the bonds in the reactants minus the energy that comes out when you form all the bonds in the products. If you get more energy that's evolved when you make the products, that's overall an exothermic reaction. This term over here will be bigger, and so then this whole thing comes out negative because of the negative sign. Okay, so this is phrased on your info sheet like this, kind of similar to how we phrased the enthalpy of formation, however with one big notable difference. And that is that here, when we're using bond enthalpies, so it says H bond here, the overall enthalpy change for the reaction is equal to H bond of the reactants minus H bond of the products. So it's initial minus final, which is different than how we've been dealing with changes for the whole chapter. So previously we were saying delta H for the reaction, when you're using enthalpy of formation values, it's final minus initial, products minus reactants. And that's what we did for all the other deltas that we've done in this chapter and this book. So conspicuously, the equation for using the bond enthalpies is backwards. The reason is because they're just phrased differently. H bond is phrased that you're going to break something, HF is phrased that you're going to form something. And so inherently there are different signs. And so the only difference between these two equations is that you've distributed a negative sign through one of them to make them the opposite sign as each other. And then rearranged it to make it look pretty. So it's reactants minus products. So again, when we do this, we're going to take the reactants and we're going to imagine that we break them apart. Break this, break that, and break it right here. And then we have our individual atoms in this kind of middle step. And then we're going to reform. Hydrogen and oxygen come together like this, they come together like that, and we make our two new products. So to break these apart, you have to absorb energy, and this is the bond enthalpy, is the energy to break a mole of these bonds. And then when you reform it, you get energy out as heat that is the same magnitude, the same size as the bond enthalpy, just an opposite sign. Instead of breaking it, we're reforming it. Now, you need to know what bonds exist that are broken and reformed, so there's a high likelihood you're going to need to at least think about the Lewis structures, if not draw them, in order to figure this out. So, count this as a good time to review Lewis structures before taking the final. Okay, so let me show this with an example. So in this one, you don't necessarily need to draw the Lewis structures, because they're pretty straightforward. You know, the Lewis structure for diatomic hydrogen is just that. The Lewis structure for diatomic fluorine is that. And then you're going to make hydrogen fluoride. And so the Lewis structure for hydrogen fluoride is just a single bond between hydrogen and fluorine. So you don't necessarily need to draw the Lewis structures for this. But I'll draw them here because it makes it a little easier to figure out. Now, when we do this problem, we think about all the bonds that are broken in the reactants first. And so in the reactants, we're breaking a hydrogen-hydrogen bond and a fluorine-fluorine bond. And so that's listed here, hydrogen-hydrogen bond, fluorine-fluorine bond. You're breaking one of each. And then from a table, you get the bond enthalpy for that. Then you think about the products. And so in the products, you're going to form two hydrogen-fluorine bonds. And so you look and find in your table the bond enthalpy required to form two HF bonds, which are right here. And then you can throw this together and use the equation. So here's our HH bond, here's our FF bond, and then we have 2 times the HF bonds, because we're making 2 of those. And so when you put all these numbers together, you get an overall answer for the enthalpy change for this reaction by looking at the bonds formed and the bonds broken. So let's compare this to the enthalpy change calculated with the enthalpy of formation values like we did in the last video. And so using enthalpy of formation values, we have now products minus reactants. Remember, it's the other way around. And well, all the reactants, the enthalpy of formation is going to be 0 because it's hydrogen gas, diatomic, which is its most stable state. The same is true with F2 gas. So we have the enthalpy of formation for HF, and then minus the enthalpy of formation for H2, which is 0, and F2, which is 0. So ultimately, this gives us 543.2 kilojoules per mole from HF. And then if we compare that to the bond enthalpy version, these are really close together. So in this example, they come out really similar. They're not always similar. And the reason why they're not always similar is because we're using average bond enthalpies to compute this. So you're giving one number to represent the same bond in a variety of different contexts. And then in different chemical structures, these bonds have slightly different energies. So when you take an average, it's not always going to be perfect for all the types of bonds you might deal with. So now another example here. We're going to use bond enthalpies to calculate the enthalpy change for the combustion of methane using these average bond enthalpies and this formula for the enthalpy change of a reaction. And if you're curious what's going on up here in the listing where it says OO double bond, I was really just being lazy and using 2 equal signs in PowerPoint. So really these should be connected as double bonds like that. So my bad for being a little lazy. So for this one, you most likely need to draw the Lewis structures of each of these if you don't have an idea of what type of bond is present between each atom. Because if it's a double bond in CO2 versus a single bond, that's going to give you a much different energy that you have to deal with. So blast from the past, here are the Lewis structures. So here's methane, CH4, and then here's oxygen. It has a double bond in it, which you need to know that it has a double bond, because in most other instances I'll give you a table that has both the value for a double and a single bond, and I want to make sure that you know which type of bond it is. And then you're going to make carbon dioxide, which has 2 double bonds between carbon and oxygen. And then you're going to make 2 water molecules, which each has a single bond. So if you go and count, you're going to break 4 carbon-hydrogen bonds. So there's a 4 that you're going to multiply the carbon-hydrogen bond by. And then you're going to break 2 oxygen-oxygen double bonds. So there's a 2 here. And then on the product side, you're going to make 2 C double bond O's right here and right here. So there's a 2 in front of here. And then you're going to make 1, 2, 3, 4 bonds between oxygen and hydrogen. So now when you go and write this out, you're going to use these values. 4 times carbon-hydrogen, 2 times oxygen, 2 times the CO bond, 2 times the OH single bond. Okay, so let's put this together into the equation. So we have our reactants first, and so there's 4 times the CH bond, 2 times the OO bond, and then our products, there's 2 times the CO double bond, and 4 times the OH bond. And then when we plug the numbers in for this, we'll get an equation that looks so. And then plugging it into your calculator, here's your first term, there's your second term. So you spend 2,654 kilojoules per mole of energy to break all these bonds, and then when you reform the bonds, you get 3,438 kilojoules per mole back. And so when you finally get the answer here, it's negative 784 kilojoules per mole enthalpy change for this reaction. And then for comparison, if you look at this same reaction using enthalpy of formation values, you'll find that the overall enthalpy change is negative 802.3 kilojoules. So sometimes these values are close, sometimes they're not. In this case, they're not. And that happens sometimes, right? There are 2 different ways to determine the enthalpy change of the reaction. The HF, enthalpy of formation values, give you a little better overall number for enthalpy change of your reaction, but you have to know what the enthalpy of formation values are. Whereas the bond enthalpies, it's a little less precise, but then it'll work on any compound where you know the structure of it. So it's a lot more flexible and applicable in that way. So ultimately, 2 different ways to determine enthalpy change of a reaction theoretically, and use whichever one is called for depending on which information you have. Okay, that's all we have for this video. Thanks for watching.